Thank you so much for the very nice introduction. Just to emphasize this, again, of course, I'm not doing the work alone. Right, we have really a nice group at BAM, and we are working together on all of these topics. And everyone that you see here, and even a few people more, some of them sitting here, are contributing to that work. Yeah, so what our main idea was using simulations for faster materials discovery. And as you all know, ab initio methods, mainly in our case DFT, is quite slow, and therefore we are increasingly developing machine learning approaches. And I think everyone or many people in the field are doing that. And training data that we've been using has been connected to the materials project. I think most of you should know that, right? That the materials project is this large database of materials properties, and it has more than 600,000 accounts, and people are using this. And from our side, we're also contributing to the workflow infrastructure there, developing tools to make sure that we can actually compute the data. Yeah. Just one example why this is necessary. If you want to compute, for example, phonons, then you have to do several DFT calculations, maybe up to several hundreds of them. And therefore, of course, you need something automatic. You don't want to force a PhD student or a postdoc through doing these kind of computations manually. And that's why we are developing workflow tools. And the one that we have been recently contributing to is Atomy2. And this is part of the materials project infrastructure. So increasingly, Atomy2 will be used in the future to generate data in the materials project. And this library is behind this. So we have interfaced several density functional theory codes just to show some of them, and also machine learn interatomic potentials. There are workflows for all kinds of different properties related to the properties in the materials project. Of course, band structures, electronic structure workflows, but also phonons, and I will later on also show other properties that we are focusing on. You might have wondered about all these workflow tools that are currently around. And we as workflow tool developers have also wondered about how they actually interact with each other, and therefore have also recently started with actually building a workflow definition that is maybe a bit more general for the purpose of sharing workflows from Atomy2 infrastructure that is based on JobFlow, AIDA, and PyIron, which are all workflow managers. And I've worked on a definition where you can actually now exchange at least simple workflows between those three workflow managers and execute them. Yeah. But now back to the main part of the topic. We actually want to find new materials, and that's why we are building these large databases and this infrastructure. And you typically see this high throughput funnel to simulate or to search for new candidate materials for experiments. So you would start from a large database of materials, for example, or of unknown materials, and then compute all these different properties that you know are relevant for a certain materials application, and then suggest a bunch of candidate materials. And this can then be the starting point for experimental work, right? We at BAM, for example, have materials acceleration platforms where we use robots for this, and this is, of course, also going on at other institutions. Such a search can be successful. I'm just showing one search for a new solar cell material from the group where I did my postdoc. And they have actually found a material and then could also synthesize it experimentally and also show that these properties actually exist in this material. But we know that there, with this kind of high throughput search, still a lot of problems. Often we suggest something and we do not end up with that in the experiment. And that's why I would like to talk about three different challenges and things that we are working on in this regard in this talk. So one problem is that for the application, very often properties are relevant that are really hard to compute. For example, if you want to compute the thermal conductivity of such a large bulk structure, it's nearly unaffordable. If you want to include defects in crystal structures or go to amorphous material, or maybe even simulate whole devices with density functional theory, that's a problem, and that's why we have to scale really to large systems. The other point is that we're very often still using very simple DFT functionals as well. And one problem that I would like to talk about is how we maybe can include magnetism by machine learning in these kind of searches. And the third problem is, if we go to a really unknown material, how can we actually figure out whether it's synthesizable, whether we can actually make it in the lab? Can we, as computational people, also help with making sure that people can actually make it in the lab? Now we start with this scaling up to larger systems. So what we are typically doing in the group is we then try to machine learn materials properties, but demanding materials properties based on the chemical bonding picture. So instead of directly going from the structure to the materials property, we compute bonding properties with the help of quantum chemical bonding analysis and use this as a descriptor for the materials properties instead. Of course, this only makes sense when this is still faster than actually computing the materials property. So it only makes sense for very demanding materials properties, for example, phonons in that case. So the kind of bonding analysis that we do is connected to this very simple molecular orbital diagram, where you typically, when you look at a molecule, can distinguish between bonding and anti-bonding molecular orbitals and can figure out bond strengths. And we also can do that in the solid state with the Crystal Orbital Hamilton Population, which is essentially a bond-weighted density of states. So you can find out about bonding and anti-bonding interactions. And if you integrate the COHP up to the Fermi level, you have something like a quantum chemical bond strength. And this is something that we're using as descriptors in our models. Just to show you why this is useful, this is an example from Akash's work. This is a material, a copper-based material with low thermal conductivity. And when you look at the copper environments, you will see they are surrounded by selenium, and these environments are quite distorted. When you then analyze this crystal orbital Hamilton population, you will see that a huge anti-bonding peak shows up in these copper-selenium bonds. And if you integrate the CHP up to the Fermi level, you will get actually a very weak bond strength. So when an atom is weakly bonded, of course, if you think about the phonons, I think it's immediately obvious that they should rattle quite a lot. And actually, you also find that in an experiment. You find large thermal displacements, so-called rattling atoms. And therefore, as these rattling atoms are known to be connected to high anomalisticity in the phonons, this is then connected to low thermal conductivity. So just with this example, I wanted to illustrate that bonding can actually be useful for machine learning of materials properties. To then actually use these bonding properties, we first had to build a workflow, and this is also part of Atomic 2. We do a DFT calculation, in this case with WASP, with a plane wave-based basis set. And then to get information about bonding, we need to project these plane waves that are delocalized on atomic orbitals. That's what we're doing with a program that's called LOBSTER. And then with that information that is now in local, that we can now use based on the local orbitals, we can then compute the crystal orbital Hamilton population and then use this for machine learning. The LOBSTER outputs itself, of course, have to be translated into something that we can then use in machine learning also. And that's why we developed a post-processing tool that's called LobsterPy. And what it does, it digests the outputs from LOBSTER and then spits out automatic plots with summaries of the interactions, text summaries, and also JSONs and other data formats. So the issue is why we need such a post-processing program in that case. We are now dealing, of course, with interactions between atoms, and therefore the outputs are a little more complex than, for example, based on for a density of or projected density of states. And therefore, LobsterPy is summarizing this information that we get from LOBSTER, and, for example, looking at mean ICOP values, and is also able to tell you about coordination environments based on this electronic structure theory. And this is then something that we can actually use also in the machine learning. So we can then directly use LobsterPy also for featurization. So we take the LOBSTER outputs and get pandas data frames based on statistics of these bonding properties. There are a few more bonding descriptors that I haven't talked about that are also available with LOBSTER. And of course, we can also generate DOS-based features, as we also have projected densities of states with LOBSTER. And this is then something we can use for machine learning. Akash has now, in his PhD, computed a bonding database with 13,000 bonding properties. 1,500 have already been released, and we're currently working on making it available to Nomad and also through the Materials project. This is ongoing work, and we hope to have this easily available soon. It's already, a part of it is already on Zenodo, so that it's available for people already. With this data, we're now able to learn other properties, because before this database, we didn't have the option to test this out. And here we are learning phonons, right? Phonons are relevant, for example, for the thermal conductivity, but of course also for temperature-dependent properties. I think that's obvious. And we already can show actually that these bonding properties improve existing models with certain phonon properties. So the one that we are learning here is the last peak, I would say, the last peak in the phonon density of state, or the maximum phonon frequency in a phonon band structure. There was already a model based on the ModNet architecture available, based on just compositional and structure-based features. So ModNet is an architecture that performs really well for smaller data sets. It has a feature selection based on mutual information and then a hierarchical neural network. And now we included the bonding properties as features here, and we are seeing an improvement of the mean absolute error on this highest phonon frequency. As this is still a simpler model, just based on statistical features, we are not yet reaching graph-based models. But this is ongoing work at the moment, and we are extending it to thermal conductivity and also elastic properties. We've also built first interpretable machine learning models, because we hope that actually the correlations are more direct based on these bonding properties than on simple atomistic or elemental features. That has been a result from a master thesis. And what we've learned here is we projected the force constants that we get from the phonon calculations on specific bonds. And that's why we are learning projected force constants. And here we've been using the CISO approach. So we've used a symbolic regression-based method to generate our features. So we construct the feature space based on simpler features with these kind of operators, and then also get equations that we can interpret. And then for the projected force constants, we actually get an equation that makes sense immediately also from a chemical point of view. The projected force constant is here proportional to the covalent bond strength and the Madelung energy which is the electrostatic contribution. So both covalent and electrostatic interaction contribute to this projected force constant, and we also get this out of our models. Yeah. Just to have a connection also to this place here, we've also used the outputs from LOBSTER in large language model-based models, or I would say actually Akash and Katharina have used this as a part of the hackathon that took place last year here at this FAIRmat hub. And as I've shown you, we have also automated text outputs from LobsterPy. And we combine, or yeah, Katharina and Akash combined them with robocrystallographer outputs, which also describe, based on geometric information, the crystal structure, and then used a large language model to again predict the last peak in this phonon density of states. And this also works quite well. They get a slightly higher mean absolute error here. But what is interesting is that adding the bonding features actually helps improving the model that is only trained or fine-tuned based on robocrystallographer data. Yeah. So just to mention this, LobsterPy and also our PyMagen implementations that are actually below our LobsterPy implementations have also already been reused for other works, for catalytic applications, or for investigating phase change materials. This was the first topic on bonding analysis, but we also have a second topic where we go at large systems. And I will show also a very simple introduction that is more intuitive than mathematically correct. We also work with machine-learned interatomic potentials, right, where you go from the structures to energies, forces, and stresses. As I talk to diverse audiences, I always show this Lennard-Jones potential to just remind everyone what actually an interatomic potential is. And now we have, of course, these machine-learned flexible versions of this, which are much more powerful. Yeah. To train them, we typically start with a reference database, as you do in machine learning, labeled most of the time with density functional theory calculations. And of course, we need to represent the potential energy surface as good as possible, right? This is actually probably the most, or one of the most challenging things to do, to make sure that you sample the potential energy surface in such a way that your ML potential is trained really well. And then, based on a certain representation of your atoms, you can then machine learn the potential energy surface. Very often, nowadays, graph-based machine learning models are used. Yeah. Then we can reach an accuracy that is similar to DFT, but we are much faster. To make now ML potentials more routinely accessible, we wanted to automate the data generation and also the fitting to make it more robust to new users. And that's why we developed a tool that's called Autoplex that is based on Atomic 2 infrastructure. And this is a collaboration with a group of Volker Deringer in Oxford who have been working with ML potentials for quite a long time. And we can now use these tools, for example, to generate general purpose potentials. And there's one workflow that is then based on random sampling of structures, the so-called AIRS approach. The random structures are generated. Then for these random structures, static energy calculations are performed. Then we train a first machine learning potential. And then that's also why we need a workflow to make it robust. We then again create random structures, but use this ML potential from the previous step to optimize them to the minimum to get a better sampling of the potential energy surface. And then we again train ML potential and repeat this cycle several times. Just to mention this, the sampling here also includes measures on the structural diversity and also the energetic diversity when we then train the ML potential. Just one example where we, or several examples actually, for which we then trained ML potentials. So this is a phase change material. And with this kind of potential, we can then, it's now automatically trained, also model amorphous materials here. And what you will see in a few seconds is the crystallization process. So this part here is amorphous, and this part here you can already see the crystalline seed, right? And you can use this ML potential to also accurately describe this kind of crystallization. Yeah, we compared this then to pure ab initio simulation. So this is now the radial distribution function from, in red, our potential. This is still a gap potential. And here the ab initio calculation. And we also compared rings that are showing up in the structures between the ab initio molecular dynamics simulation and also the gap simulation. So that we can actually, with this automatically create tool, also describe amorphous structures very well. This is another example where we train in potential for titanium dioxide, right? We start with these random structures, just as a reminder. And then we perform DFT evaluations as part of this automatic process. And then after a few thousand steps, we are able to get the energies of known phases of titanium dioxide very accurately, right? And we do not put these structures in, or at least not on purpose, in our training data. That's, I think, the important thing. We start with purely random structures and then are able to recover these energies for known phases. And this, of course, also then enables exploration of completely new phase spaces. Same for a whole composition, titanium oxide. Here we tested different titanium oxygen phases. And again, after a few thousand steps, we're able to recover and get good energies for these known phases. So yeah, now we've built a potential, a specific potential for a certain composition. But you've probably also heard about the foundation ML interatomic potentials, or maybe pre-trained ML interatomic potentials that can be used for the whole periodic table. There's quite a lot of interest in these ML interatomic potentials, so people are picking them up, and you've seen probably that there are tons of new releases. In a phase there was basically a new release every week. The field is really interested in using them. And one thing we found surprising was actually, as these ML potentials are typically trained on these inorganic materials databases, that they can actually be used also for other purposes, and you get qualitatively the correct results, simulations out of these potentials, and that they are really generalizing beyond inorganic materials. But of course, they are not perfect, right? And this also brings me back to our infrastructure to build ML interatomic potentials and also to fine-tune interatomic potentials. So we now took this Maze MP0 model, took here one crystal structure that we are interested in, and as you can see, for this specific crystal structures, for example, imaginary modes are not covered very well, so it could use actually some improvement, right? And therefore, the fine-tuning approach is something that we and many others have been interested in, where you take the original ML potential, add smaller, more specialized data set, and then get and adapt the weights of your ML model to that smaller data set and get a new one out. If we are able to control this very well, of course, this promises a massive speed up than training, of course, ML potentials from scratch. And we've started also to implement these kind of procedures as a part of Autoplex. For phonon properties, we can already train these automatically. Just want to now show an example where just 8 additional supercells have been added to the training data here. This is based on transfer learning. So if you might remember the picture from before, maybe not, but I tell you that the higher phonon frequencies are now better treated, but it's still not perfect. So transfer learning alone will probably bring us not to a very good solution. And in some cases it works, but in this case not. But of course, we can also use other options. In this case, the so-called multi-head fine-tuning option was used. And then for the phonon properties, we're actually able to recover these imaginary modes. There's still some problems with this fine-tuning here because the fine-tuning itself takes a lot of time still. And therefore, what I wanted to show in this part here is mostly that we still have to figure out efficient fine-tuning procedures. And this is still, I think, work in progress for many groups at the moment. But nevertheless, I think automation can help with this. And I also want to show one automatically fine-tuned example here for a phase transition. Beta tin is known to have a phase transition to alpha tin. We can also describe this with DFT. But when you take maze MP0 and try to describe this phase transition and the Gibbs free energies, you will actually see there's no phase transition. When you fine-tune for a bit, in this case, this was the transfer learning approach, you can actually get a phase transition. And again, this was only done with a few Breton structures. Nevertheless, I think a lot of work has to go into finding robust solutions for this and exploring these kind of things. And therefore, automation, I think, can also really help here. Yeah. So summary of that part. So bonding properties have predictive power for materials properties. Machine learned interatomic potentials are really powerful tools for predicting materials properties. I think fine-tuning can be really promising once we have robust recipes for that. And workflows have been really central for doing these kind of things in our case, and we had to develop these tools to be able to do this kind of research. Now I'm going to the other point, right? Very often we actually exclude magnetism from our material searches because it's not easy to describe. With DFT plus U is really poor. This can be okay, but if you have a fixed U value, it can be a really poor description. And that's why we have been looking into, maybe finding other ways to predicting this kind of magnetism. Here we focus on transition metal oxides. This is a project by Katharina, and we try to go from the structure to the magnetic structure. But the data source in that case is an experimental data set. It's the Magen data set, which is based on neutron diffraction data and which has several thousand entries. There are, of course, also problems with experimental data sets. But nevertheless, we use this as a starting point. Just to mention this, in typical DFT calculations, we very often do not include non-collinear magnetism because it's also complicated. But of course, in this database, it shows up. We do not only have ferromagnetic and antiferromagnetic collinear magnetic structures, but also those that show non-collinear magnetism. So where the spins are not aligned to each other with 0 or 180-degree angles, which makes the machine learning a bit more complicated. Yeah, so as I said, we focus on transition metal oxides. And maybe you remember from solid-state physics courses, there are actually heuristics rules for transition metal oxides and the magnetism. So the so-called good enough Kanamori rules. And what they do is they connect the transition metal oxygen transition metal angle to the kind of magnetism that shows up in the transition metal oxides. So for example, in the 90-degree case, you typically have ferromagnetic interaction. In the 180-degree case, you typically have antiferromagnetic interactions. And we thought, we wanted to use these kind of relationships, of course, also in our machine learning model. And that's why you also see why we need to do this kind of featurization. We cannot use simply a graph-based models. We only have 450 structures, right? So we cannot build a graph-based machine learning models. We don't, and based on neural networks, we just have not enough data for that. And that's why we started here. We took 450 structures and then determined oxidation states based on heuristic, then looked at coordination environments with a different approach that we'll talk about, and then focused on the magnetic sites and their connections, and used this for featurization, but also for testing the heuristic. ChemEnv has been an algorithm that has been developed to get these coordination environments. I just wanted to shortly introduce what it does. So when you have a very distorted coordination environments, local environment, assigning names, what kind of polyhedra you have, is not very easy and straightforward. And that's why ChemEnv has been developed. And you start with a Voronoi construction here to select neighbors. And then based on some distance and solid angle cutoffs, you're able then to select which atoms are actually neighboring to this one here in the middle. So for example, we have a minimum distance here, and then kappa times this minimum distance is our cutoff, and all atoms that are further away are not considered as neighbors anymore. Similarly, we can define something based on the solid angle in such a construction. And then we have coordinates that can be compared to ideal shapes in a mathematical equation that describes a so-called continuous symmetry measure, which is a distance to a shape. And then we can actually assign coordination environments and also use this in machine learning approaches. This has been in PyMagin for quite a while, as this is actually some work from my postdoc time. I've written a tutorial for that. We also have a web application for using these kind of tools. And this data is also, at least for simple ionic compounds, available on the Materials project since 2 years. So we now use these kind of tools to test, first of all, these good enough Kanamori rules on our data set. So we look at all ferromagnetic interactions and then check the bond angle. So for ferromagnetic interaction in transition metal oxides, you really have this peak at 90 degrees. For antiferromagnetic interactions, it's not that easy. Of course, you can imagine as these good enough Kanamori rules are based on super exchange, other exchange mechanisms might play a role here. And that's why the picture for the antiferromagnetic case is not that clear. So you also have still a peak around 90 degrees and higher bond angles showing up. But what we can say when we do a statistical test is that these distributions are actually different. So there is really an influence of the bond angle on the transition metal oxides, also based on the statistical analysis. And now we try to use this kind of idea, of course, also in our machine learning model to learn the magnetism and the magnetic structure. Unfortunately, we have only 450 data points. We cannot learn all spin states in such a structure, not possible. And that's why Katharina came up with a different way to describe the spin states and also include a descriptor for non-collinear magnetism. And what we do here is we count how parallel actually these spins are to each other. So for example, we have this atom here with a certain spin state, and then we look at the neighbors, how many neighbors are actually parallel and how many are anti-parallel. And our parallelity score in this case says we have 2 parallel, and then we divide it by the total number of neighbors, which is 3. And then we have for the specific side 2/3 as a parallelity score. And then we average this over all neighbors. And this is then what we are learning. Same for an anti-parallelity score. This is really to take care of the non-collinear magnetism, as we cannot simply learn ferromagnetic and antiferromagnetic as labels. And then we can actually learn the parallelity. And also the antiparallelity. You might be confused why this is actually, it is a descript or a measure for a classification that is showing up here. We unfortunately also had to, couldn't use a regression, but we also had to transform this into a classification problem where we learned extreme P and AP values. But yeah, with this classification approach, we can actually learn this parallelity and also the anti-parallelity score. And then also these models are significantly better than the baseline that just comes out of our training data set, as it is quite biased. Yeah. And with this, we can now search for new collinear and non-collinear magnets, and also for new ferromagnetic compounds, because this is included in our parallelity and anti-parallelity score. And what we can also check is what is the role of this heuristic. So we can also check the heuristic on the machine learning model. And what we did is we trained one model with features, with all features, and then one model without those that are connected to the heuristic, so the bond angle determining the magnetism. And we can actually see a significant difference between the models. So the bond angle and related features are really predictive for the magnetism in these compounds. So what I wanted to show here is that the data is really important that we're working with. And we very often still have low data scenarios. And in this case, we actually trained a random forest-based model. We couldn't do anything graph-based because we didn't have the data. And in such cases, of course, these crystallographically motivated descriptors on the geometry of crystal structures might be really useful. And yeah, in this case also, we can confirm that bond angles are actually important for the magnetism in transition metal oxides. Yeah. Now I'm coming to the last topic. And this is now going about synthesizability, right? In case we have now decided on a new structure, the question, can we actually make the material? Yeah, very often are using to decide this, of course, the formation energies as a function of the composition, right? You put in all known phases and their formation energies, and then when you have a new phase, you check how far away you're from the hull, right? But I think it's immediately obvious temperature effects are missing, but also the way to go there, the technology is missing. So this is maybe not, yeah, it's very often shown to be not a completely successful approach. And then we can actually use a different approach that has been introduced by Yusung Yang. And what it does is it starts from the database of known synthesized materials and a realistic set of candidate materials where we do not know that the material actually has been made or not. In this case, we actually do not have a negative data set. We cannot really use this because we do not know which materials cannot be made. And therefore, here we have a PU learning approach. And this works like this. You start with a data set with positive and unlabeled data. Then you randomly assign negative data points from the unlabeled ones, train a classifier, predict the remaining labels, record those, and repeat this 60 times. And then by averaging, you can then define which of them are of the unlabeled, which of them are positive and which are negative. Sorry. But one problem is that we actually do not know how a perfect model architecture for this should look like. And that's why we actually went beyond this PU learning approach and introduced dual training in that case. So we used two different graph-based machine learning models, Schnet and Align, and we did co-training. How does it work? You start with this initial PU training data set, put that into the first PU learner, and then based on the results from that PU learning approach, you extend these unknown labels by the positive ones predicted by this PU learner, and then this is the input to the next PU learning, and then you again extend the positive labels and so on. And then in this way, we can actually improve the results of our models. So here we started with a line, perform PU learning, extended the positive labels, put that into Schnet, and so on. And then we see overall an improvement of our measure for the machine learning model. Yeah, we had two different ways of measuring here, in this case, the recall. One averaged over the PU learning steps, and one leave out set that we separated out at the beginning. Why are we only showing recall here? Yeah, the issue is we only know about the positive data, so we cannot measure precision, and therefore only recall is actually here our measure. One thing, of course, that's still open to me, how are these models actually then connected to what we know chemically intuitively? And we see with these models that we can improve, of course, the synthesizability prediction, but I would also like to then connect this again to chemical knowledge. Yeah. Summary. So this funnel approach to search for new materials can be successful, but still has several drawbacks. One problem is that we very often actually need to scale to large systems, include defects, amorphous structures, that we might go beyond simple DFT approaches and also include magnetism into these predictions, that we don't really have a solution yet for synthesizability. ML interatomic potentials are at least really helpful for large systems. And in all of our studies, at least, well, nearly all of our studies, workflows will be a key ingredient to make this research possible. Yeah. Now, I just wanted to mention that these tools that I've mentioned in passing are all open. We have tutorials available for each of them. You can pick them up. Autoplex, Atomy2, and LobsterPy. And I would like to thank everyone that works with me on these projects, and especially the group that I'm working with at BAM, who has done the most of the practical work. Thank you very much.